Going to wait to save streaming. I'm gonna stay here for 1.5 hours today. I'm gonna start by doing the Italian thing, I think. The last article that I have to finish is the minimal vertex cover. And I did the two-tape polynomial offstream. And I also decided to do some articles about linear algebra as I was doing the two-tape polynomial because I thought, why not, since I'm already going to have to review those concepts and study them to be able to understand the two-tape polynomial. Then I decided to do the other articles. And most of the stuff was things that I already know, but because the way that is written is kind of confusing to understand. Like it seems more complicated than it actually is. So as I was doing the articles, I realized that it's actually very simple. The whole explanation of what a matroid is, and then to understand matroids, you need to understand linear combination and linear independence. And I'm gonna explain these things, what I figure out after I do this Italian thing here.
Fa,
Fa,
Does.
fisso,
fisso,
Set. Unchanging.
3,
3,
3.
desiderare,
desiderare,
Desire.
aria,
aria,
Air.
bene,
bene,
Well.
anche,
anche,
Also.
giocare,
giocare,
Play.
piccolo,
piccolo,
Small.
fine,
fine,
End.
mettere,
mettere,
Put.
casa,
casa,
Home.
leggere,
leggere,
Read.
mano,
mano,
Hand.
portare,
portare,
Carry.
grande,
grande,
Large.
compitare,
compitare,
Spell. Words.
aggiungere,
aggiungere,
Add.
anche,
anche,
Even. Also.
terra,
terra,
Land.
qui,
qui,
Here.
devo,
devo,
I must.
grande,
grande,
Big.
alto,
alto,
High. Tall.
tale,
tale,
Such.
seguire,
seguire,
Follow.
atto,
atto,
Enact.
perché,
perché,
Why.
chiedere,
chiedere,
Ask.
maschi,
maschi,
Men.
cambiamento,
cambiamento,
A change.
è andato,
è andato,
He. She went.
luce,
luce,
Light.
tipo,
tipo,
Kind. Of thing.
spento,
spento,
Turned off.
bisogno,
bisogno,
Need.
casa,
casa,
House.
immagine,
immagine,
Image.
provare,
provare,
Try.
noi,
noi,
Us.
di nuovo,
di nuovo,
Again.
animale,
animale,
Animal.
punto,
punto,
Point.
madre,
madre,
Mother.
mondo,
mondo,
World.
vicino,
vicino,
Near.
costruire,
costruire. What the fuck was that?
Build.
se stesso,
Se stesso,
Himself.
terra,
terra,
Earth.
padre,
padre.
Father.
I don't know what happened there. That stopped out of nowhere. I think I'm gonna put some music and then I'm gonna explain the thing first. and then I'm gonna study the minimum vertex stuff. And if I have time, I already did all of this here with ChatGPT. These data structures, I'm gonna finish these ones. I decided to remove most of the data structures that were related to trees or variations of trees, because I wouldn't do them anyway, I think. I'm only gonna do them if I encounter something that I think is relevant and is related to a data structure like that, because otherwise I think it doesn't matter that much it's not relevant to do articles about them, because there's so many different articles that I had to write about so many different things. So it's gonna take a long time until I'm probably never gonna run out of ideas, I think, to write articles, especially with all the categories that I wanna write articles about. So yeah, but I have these ones that I already made and then that I need to review only. And yeah, after I finish the minimal vertex, I'm gonna start with these ones, which are the main data structures, are most useful. And then I'll go back to writing stuff about algorithms. I think I'm gonna do 10, at least 10, or probably I'm gonna do 10 for each category, if there is 10 variations of the other, like trees. Then there are other things that I forgot. I need to remember that I think I wrote down and I have them on a list of categories of different algorithms. And I stopped on this one, skip this. So pretty much the idea, linear combination is just a combination of vectors. So you have the x, y, and z coordinates, and then you can use these coordinates to create any vector you want. And then usually you create the smallest size of a vector, which is a unit vector. And then you represent other vectors in relationship to that unit vector by multiplying them by a scalar. And then this multiplication and addition of different vectors is called a linear combination. And the concept of linear independence is when you have a linear combination, when you can have one of the vectors be equal to a linear combination of the other ones, or if the linear combination of them is equal to 0, as far as I understand now. And then all of that a matroid is just an exemplification of that to sets. So methods are to sets what linear independence is to vectors. So it's pretty simple to understand if you think it like that. But reading this stuff, it gets complicated because they use a bunch of different words, and that's the kind of stuff that turns me off about mathematics. Is usually like this, where they seem to overcomplicate things, probably because most of the resources you have to write in this language, because it's probably a convention to write it like this, using all the symbols. Yeah, but it just gets it overcomplicates things that are relatively simple to understand. So that's all that a matroid is. And then in the context of graphs, what a matroid is used for is to abstract the properties of a graph into a polynomial. So the notion of independence in a graph when it comes to matroids means that you don't have any cycles. And if you have dependence on the graph, that means that it's the cycle of a graph. So the dependent parts of the graph are cycles when it comes to matroids, and independence is when you don't have cycles. And then all that up to the polynomial is the exemplification of the graph into this polynomial that allows you to see these properties of the graph based on what the polynomial is. So it's kind of like you're creating a rule set to abstract the information of the graph into this polynomial, and that's effective because then it becomes much more efficient to analyze bigger graphs, because you can just look at the polynomial. And the whole process of the algorithm is shrinking the graph gradually into subgraphs by deleting the edges and the nodes at each step and making the graph smaller and smaller, while adding the information to the polynomial. And that's what this graph here does through the recursion. You get subgraphs, and then you call the function recursively with the subgraph. And this is the formula for the total polynomial. And you can choose different formulas, as far as I understand, for depending which application or which information you want to encode about the graph into the polynomial. And then the base layer, the base case is when the graph doesn't have any nodes or vertices, that's gonna return 1. And then because it's calling recursively, it's gonna go back to the stack frames that it had before and replace the value with 1, and then do it like that in a recursion kind of like creates a tree, and then when you reach the bottom of the tree, it goes back and solves the previous ones, and then it goes deeper again with the new solution to solve the other calls, and it goes like that until it gets to the final value. That's pretty much how it works. So I created the three different articles here in linear algebra, and I think I might do them sooner, but I think I want to do articles about the blockchain first before I go back to this. Because I think what I'm gonna do is probably do articles about linear algebra before I start writing stuff about machine learning and artificial intelligence. But it's gonna take a long time to get to the point, because I wanna have a bunch of different articles on the first main two categories. And I might do articles about the other categories as well before that, about economics and health and fitness as well. Because there's a lot of stuff to talk about there as well. Subset of vertices such that each edge in the graph is instant to at least one vertex in subset. First thing that I'm going to do is replace this, which I've been doing so far, with nodes, because I think that writing as nodes and nodes is easier to someone that is new to understand. Vertices can be confusing, because a person might not know that they are the same thing. So I'd rather replace everything with nodes. This one's gonna be really hard. Maybe I should leave Vertex on this one because it's the name of the thing. So I just change the vertices to nodes instead. So I might not be able to finish this today because I remember taking a look at this in the past before I did the tutti polynomial one, and it's quite hard. Seems quite hard to understand. I don't really understand what that phrase means exactly. Like, is it just when all the nodes are connected to at least one edge? At least this one seems easier to find information than metroids and tutti polynomial. Graph theory, a vertex cover, sometimes node cover, of a graph is a set of vertices that includes at least one endpoint of every edge of the graph. What's just one endpoint? Isn't that always the case though? Yeah, I want to find a situation where that's not the case, so I understand. I guess if you start from this node, for example, and then you stop here, then obviously this node is not connected to everything else in the graph. But it seems like the only possible case for having the minimal vertex cover would be to have the whole graph, since every node has to be connected on once with the edge. That's what I don't understand about this. I think I've studied this on the past on one of the algorithms, pretty sure about this. Yeah, I don't understand this definition. Size vertex cover. I think I'm gonna have to watch some videos, hopefully there.
Today, we're...
And for our next MP.
Now we turn to the concept of a vertex cover, which...
This is the stuff that I'm talking about a lot of these problems, that not that they are hard to do necessarily, is that it's more that it's difficult to understand what people mean when they are talking about this.
Which will play a role analogous to the one played by the concept of minimum cut in our discussion of maximum.
Or when you're solving the problem, it's hard to think about it on how to structure the solution. Like how to structure the problem, how to structure the graph that you're going to use, and then how to structure the solution based on the way that you structured the problem. I think that's the hard part. Like once you understand what people mean when they say certain things and how the problem is structured, then it becomes easy to solve.
Flows.
Given a graph G, we say that S is a vertex cover if every edge is incident on a vertex in S. Thus, we say that S covers all the edges. Take this graph, for example, here. If we include this vertex, then we cover these three edges. Including this vertex covers these three more. Adding this vertex includes these more edges. And lastly, we need to cover this edge here, so we'll add this vertex here as well. One pretty easy observation to make about a vertex cover is that its size serves as an upper bound for the size of a matching in a graph.
Okay, so it's the minimum amount of nodes that you need to have in order to cover all the edges of the graph. I think I get it now.
As stated in the proposition here. The proof is simple. Clearly, for every edge in the matching, at least one vertex must be in the cover. And of course, all these vertices must be distinct because no vertex is in two matched edges.
Everyone, in this video, we're going to talk about the two approximation for the vertex cover. Now, a vertex cover of a
I
connected.
think I'm gonna write this down and I'm gonna replace the stuff here. Yeah, so this I'm gonna keep here. I think this part I'm gonna remove because it seems redundant. Minimum vertex cover in a graph is the minimum amount of nodes you can choose in order for them to contain all of the edges of the graph. In other words, it is a set of nodes that cover all the edges in the graph. The algorithm will provide. Yeah, I think this part is good.
The undirected, unweighted graph G is a subset of vertices V of G such that for every edge in G, at least one of its endpoints is in V. A minimum vertex cover is the vertex cover that has the smallest cardinality, or the vertex cover which has the smallest size. In the two approximation algorithm for the vertex cover, we're trying to find a vertex cover which is at most 2 times the size of the minimum vertex cover. So let's go through this algorithm in detail in a step-by-step manner. We start off with the empty vertex cover, that is, the vertex cover V is initially empty. Then we consider any edge in this graph. Let us consider the edge between 0 and 2. We next consider both these vertices 0 and 2 and add them to the vertex cover. We also remove all edges that are incident on either vertex 0 or 2. As you can see, there are only two edges that are left in this graph, the edge between 3 and 1 and the edge between 1 and 4. We next pick any one of these two edges. So let us pick the edge between 3 and 1. What we do is we add the two vertices 3 and 1 to the vertex cover and remove all the edges that are incident on either 3 or 1. With this, we actually come to the end of the algorithm because we see that all these edges are now covered and the vertex cover comprises of the vertices 0, 1, 2, and 3. This is the two approximation algorithm for the minimum vertex cover. Thank you for watching.
Friends, in today's lecture, we will understand what is vertex cover problem. Let's start. Vertex cover problem. In the mathematical discipline of graph theory, a vertex cover, sometimes node cover of a graph, is a subset of vertices which covers every edge. An edge is covered if one of its endpoints is chosen. In other words, a vertex cover of a graph G is a set of vertices incident to every edge in graph G. In the vertex cover problem, we have to find what is the minimum size of vertex cover in G. Vertex cover is a greedy algorithm, and the basic idea behind this is we have to find a vertex which covers the maximum number of edges. We can use simple steps to find the minimum edges. Find the vertex, step 1, find a vertex V with a maximum degree. Step 2, add V to the solution and remove V and all its components, incident edges from the graph. Step 3, repeat until all the edges are covered. vertex cover problem is an incomplete problem, means it takes polynomial time to complete the algorithm. A true approximation polynomial time algorithm is as follows. Approx vertex cover G. C is a set of pair consisting of a graph and a positive integer. Phi is null set. E dash is a set of edges, and G, comma E, comma V. G is a graph which contains the edges E and vertex V. We start the while loop. E dash not equal phi, and we have to randomly choose a edge U, comma V in E dash and put U and V into C. Remove all the edges that covered by U or V from E dash and return. At last we have to return C. Here is the proper algorithm for vertex cover. C is a set of pair consisting of graph and positive integer. Phi is null set. E dash the edges we are considering is the set of edges. By E dash not belong to phi. Let U be an arbitrary edge of E. Remove all the E dash all the edges incident of the U or V, and then we have to find phi. Here is the problem for the vertex cover. It is given an undirected graph, and we have to find the vertex cover with the minimum size. In the graph, we can see that there are 7 vertex and 7 edges. Let's start by finding it. Vertex cover. In the first step, we choose the edges vertex 1 and 2. We can see that it is covering the 4 edges, but edges 5, 6, 3, 6, and 3, 7 are not covered by it. So it is not a vertex cover problem. It is not the final vertex cover. Now we have chosen vertex 1, 2, and 6. We can see that edges 1, 4, 2, 1, 2, 5, 5, 6, and 3, 6, and 2, 3 edges are covered, but the edge 3, 7 is not covered, so it is not the vertex cover. We continue the loop, and we have chosen the vertex 1, 2, 6, and 7. We can see that all the edges are covered by this vertex, and the size is 4. But there is possibility that there are minimum vertex can be found more. So we will continue in the loop. In the continuing value, we have chosen the edge vertex 1, 5, 3, and we can see that all the edges are covered and the minimum number of vertex is taken, like edges 1, 4, 1, 2, 2, 5, 5, 6, 2, 3, 3, 6, and 3, 7. All the edges are covered, and here is the minimum number of vertices we have found, and we have covered all the edges. Minimum number of, so it is about the final answer, a minimum number of vertex cover. Let's conclude. A set of vertices such that each edge of a graph is incident to at least one vertex of the set is called the vertex cover. It is a greedy algorithm. A greedy algorithm may or may not produce an optimal solution. Approximation algorithm does not always guarantee optimal.
The complete problem, which will be vertex cover. A vertex cover is a subset of the vertices of the graph, exactly what we had before. But here, a vertex cover requires that every single edge in the graph, at least one of its vertices, must be in our vertex cover. This is different than our previous problems because we want this set to be small to make it like optimal in a sense, because a vertex cover, that one will be every single vertex of this graph. Of course, we have every single edge covered by doing that. Let's get some easier ones. Let's get V1, V3, V5, V6, V7, and V8. So I need to check every single edge. That's touching blue, 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 blue. Every single edge is touching a blue vertex, therefore this is a vertex cover. I need that every single edge touches at least one blue vertex. It can touch multiple. Notice that this edge touches multiple and this edge touches multiple. So we're going to follow one. Well, let's try and remove some of these and see what we can do. What if I look at V2, V4, V5? V2, V4, V5. So let's check all the edges. That touches a blue node, a blue node, a blue node, a blue node, blue, 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 blue. Yeah, the vertex cover. Let's check on the flat. So we have V2, V3, V8. V2, V3, V8. That touches one. Oops, that doesn't work. So V1, V5 breaks it, let's say. We have V1 and V5 both are not in V prime, so that's not a vertex cover. So it's a vertex cover. Let's see what we can do with our proof. We have to say the problem first. The problem is, given the graph G and an integer M does have a vertex cover size, exactly what we just saw before. To prove that it is a NP problem, we just need to verify it. So give me a solution needs to have the correct number of elements, and for every single edge, I need to check whether or not one of its vertices is in the graph. There are big old N edges, and there are big old N vertices in V prime, so if I loop over both the number of edges and the vertices, big old N, clearly polynomial N. So it's NP. This is going to be very easy, like I said. Now, we need to show we can do a reduction. Our reduction we're going to do here is going to be reducing an independent set problem to the vertex cover problem. Let's check why this is the case. Let's suppose we have an independent set. If I have an independent set like V1, V3, V6, V7, V8. Let's look at the other vertices that we have not highlighted. V2, V5, V4. First, let's check this is an independent set. This does not touch any blue vertices. 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 So the blue nodes are an independent set. And now, if we look at the red nodes, this edge is covered. This edge, that edge, that edge, that edge, that edge. Huh. That's exactly the vertex cover we looked at earlier. So let's say we have an independent set. We find the complement of everything that isn't in that set, and that will be a vertex cover. So these look like their opposites. And just like we saw before, we prove this is an if. I prove one way. I will leave it to you to prove the other way. So I'm going to say if we have an independent set, then V minus that independent set is a vertex cover. Let's prove it. So like we saw before, we're going to start with an independent set, and then just use our definition. So our independent set, V prime. We're going to define what V minus V prime is. So we talk about it. We're going to call it W. If UV is an edge, then by definition, at least one of those can't be an independent set. Because if it was, let's go up here. Let's say UV is an edge, like this one. If both the independent set. So if this is an edge, then at least one of U or V are not in V prime. So if one of them is not in V prime, we have that U must be in W or V must be in W because it is the complement. If it's not in V prime for any edge, we must do some transformation to turn it into a instance of the vertex cover problem. To do this, we're going to say that if we have an independent set of size K, then we have a vertex cover of size N minus K. Do this exact methodology. We could say exactly what the solution is. We don't care though, actually. All we care is that if we have an independent set, then we have a vertex cover of the correct size. So if I have an independent set of size K, I have a vertex cover of size N minus K. I can directly map this. I can map K to N minus K. Notice G stays the same.
Yeah, so this is related to the polynomial if you think about it, because it's the same thing. Like finding the minimal vertex cover is the same as finding the independent sets in the matroid of the 2D polynomial.
So if I have an independent set, if and only if I have a vertex cover, then these problems are the same. The yeses map to yeses. And I can reduce this thing in n plus m time by just copying the graph and doing arithmetic. So this is clearly a polynomial, and the reduction is relatively straightforward. You just look at the complement of the set of vertices that are in the independent set, which we didn't include here. That was part of our lemma. But there's an independent set if and only G stays the same. So if I have an independent set, if and only if I have a vertex cover, then these problems are the same. The yeses map to yeses. And I can reduce this thing in n plus m time by just copying the graph and doing arithmetic. So this is clearly a polynomial, and the reduction is relatively straightforward. You just look at the complement of the set of vertices that are in the independent set, which we didn't include here. That was part of our lemma.
going to introduce vertex covers. We'll talk about the definition, see some examples, and see a couple of results concerning vertex covers. If you're familiar with edge covers, this is a very similar concept. A vertex and incident edge are said to cover each other. So for example, looking at this 4 cycle down here, the edge v1, v2 covers v1 and it covers v2. But we could also say that v1 covers this edge, and we could say that v2 covers this edge. So then a vertex cover in a graph is a set of vertices that covers all edges of the graph. Again, looking at our 4 cycle, if we were to include the vertices v1, v2, and v3 in a set, together all 3 of them cover the graph. So this is a vertex cover. Every edge in the graph is covered by at least one of these vertices. So remember, a vertex cover is made up of vertices, and they are covering the edges. An edge cover is the other way around. An edge cover is made up of edges and covers the vertices. But today we're talking about vertex covers. One thing you might notice about this vertex cover is that we don't actually need all 3 of these vertices to cover all the edges. If we removed v2 from our vertex cover, we would get a smaller vertex cover. This edge and this edge are covered by v1, whereas this edge and this edge are covered by v3. So this is indeed a vertex cover of the graph. Every edge is incident with at least one vertex in the set, so it is a vertex cover. Furthermore, now it is a minimum vertex cover. It's a minimum vertex cover because there's no other vertex cover of this graph with fewer vertices. There is another minimum vertex cover. Instead of v1 and v3, we could use v2 and v4 to cover all the edges, but there's no vertex cover with fewer than 2 vertices. So this is a minimum vertex cover of C4. And the number of vertices in a minimum vertex cover is called the vertex covering number of the graph. So here we see that the vertex covering number of C4, the 4 cycle, is 2, because its minimum vertex covers have 2 vertices. And this notation is not universal, but it's used in my favorite graph theory textbook. Beta of a graph is used to denote the vertex covering number. So beta of C4 equals 2. And we might as well go ahead and do some color coding here. We'll make the vertex covering number words and the notation the same color. Let's make them blue. So again, the minimum number of vertices in a vertex cover of a graph is the vertex covering number of the graph. And a vertex cover with this minimum cardinality is called a minimum vertex cover. So again, this is a minimum vertex cover. It has 2 vertices. That's the minimum needed to cover this graph. And so its vertex covering number, denoted beta of the graph, is equal to 2. For another quick example, we could look at the 5 cycle. If we include the vertices u1 and u3 in a vertex cover, we'll have almost all edges covered except for this one down here. So we're going to need one more vertex. Doesn't matter if we include u5 or u4. Let's say we include u5. Then this vertex subset containing u1, u3, and u5 is a vertex cover of C5, and it happens to be a minimum vertex cover. Now, since this is a minimum vertex cover with 3 vertices, what can we say about C5? Well, since the minimum number of vertices in a vertex cover of C5 is 3, 3 is the vertex covering number of C5, and so we can write that beta of C5 is 3. That's the vertex covering number. In general, what do you think the vertex covering number of a cycle graph is? Take a minute to think about it, and then I will give you the answer. All right, let's first consider cycle graphs with an even number of vertices. So the vertex covering number of Cn, but we'll write over here n even. Remember that every cycle graph is 2 regular, so every vertex covers 2 edges, and a cycle graph has as many edges as it has vertices. So if it has an even number of vertices and each vertex covers 2 edges, then all we need is half the total number of vertices to cover all edges, right? Looking at our example C4, there are 4 vertices, 4 edges. Each vertex covers 2 edges, so we only need 2 vertices, half of the total. Now coming over here, what about if n is odd? Then what can we say about the vertex covering number of Cn? Well, in general, the definition of an odd number is that it's equal to 2k plus 1 for some integer k. Again, since the cycle is 2 regular, k vertices will cover 2k edges. But if we have an odd number of vertices, we'll have an odd number of edges, and so there will still be that plus 1 edge left over. And so we'll need an extra vertex to cover that extra edge. And counting that number of vertices that we'll need can be accomplished by, again, dividing by 2, but now rounding up. So this is the ceiling function, which rounds the number to the nearest integer greater than or equal to it. Looking at our 5 cycle, 2 vertices are enough to cover 4 edges, but there's 1 edge left over, so we need 1 more vertex to cover that edge. That's 3 vertices, which checks out with our formula. The ceiling of 5 over 2 is 2.5 rounded up to the nearest integer greater than or equal to it, and that's 3. But now the next thing is, when n is even, the nearest integer greater than or equal to half of n is half of n, because when n is even, half of n is an integer. And so in general, whether n is even or n is odd, the vertex covering number of the cycle graph on n vertices is the ceiling of n over 2, the ceiling of half the order of the graph. When n is even, that ceiling function isn't going to change n over 2, and when n is odd, that ceiling function will round it up just like we need. Now here's another way we could state the definition of a vertex cover. It's equivalent to our previous definition, but the way this one is stated I think helps illuminate the next point I want to make. Let G be a graph with vertex set V and edge set E, and then take a subset X of the vertex set. If UV being an edge implies that at least one of the vertices is in X, so U is in X or V is in X, then X is a vertex cover of G. Again, this is just saying that X is a vertex cover if every edge of the graph is covered by vertex in X, because this part says in order to be a vertex cover, an edge being in the graph implies that at least one of its n vertices is in X, so the edge is being covered. Then what I want you to think about is what happens if we take the complement of a vertex cover. The complement meaning the set of all vertices not in the vertex cover. Well, if you think about it a little bit, you may come to the conclusion that here's the answer. The complement of a vertex cover is an independent set. Independent vertex sets we've talked about before. I'll leave a link in the description if you need a recap. It's just a set of vertices, none of which are adjacent to each other. If we go back up to our 5 cycle, we can see an example of an independent set. This vertex cover right now is not an independent set because U1 and U5 are adjacent. But if we got rid of U5, this would no longer be a vertex cover, but it would be an independent set. A set of vertices, no 2 of which are adjacent. Now, why is it that the complement of a vertex cover is an independent set? Well, in order for the complement to not be independent, it would have to have 2 vertices that are joined by an edge. But if the complement had 2 vertices that are joined by an edge, that would have meant that the vertex cover didn't have either of those vertices. But that would then mean that the edge joining them isn't being covered, which would mean that it wasn't a vertex cover in the first place. So the idea is that a vertex cover, by definition, is always going to have at least one of the vertices incident with each edge. And so when you take the complement of that, you're not going to get 2 vertices that are joined by an edge, because a vertex cover had to have had at least one of those vertices. Thus, the complement can't have both, and so it will be an independent set. We'll do a rigorous proof of that in a future lesson, so don't sweat it if you don't understand that completely, but take some time to think about it. But let me take you along a little further. If we take the cardinality of a vertex cover, so just the number of vertices in it, and add the cardinality of the complement of the vertex cover, what are we going to get? Well, by definition, the complement consists of all the other vertices. So total, that would be all the vertices in the graph. And so the sum would equal the order of the graph. Then if we were to take the number of vertices in a minimum vertex cover, which is denoted beta of G, the complement of that minimum vertex cover, you can imagine would be a maximum independent set. The notation for the cardinality of a maximum independent set, you may recall, is alpha of G. This is the vertex independence number, the number of vertices in a maximum independent vertex set. So once more, the idea is if we take the cardinality of a minimum vertex cover, that is by definition the vertex cover number, beta of G. The complement of that, you can imagine, we're not proving it, we will in the future, but you can imagine that the complement of a minimum vertex cover would be a maximum independent set, the cardinality of which is the independence number of the graph, denoted alpha of G. Then since we said a vertex cover and the complement of the vertex cover contain all the vertices of the graph by definition, we have that the sum of these two things is equal to, we might say, n, the order of the graph. So that is a nice result that we'll prove in a later lesson. I'll leave a link to it in the description. The vertex covering number of the graph plus its vertex independence number equals the order of the graph. All right, one last thing, try these on your own. What do you think the vertex covering number of a complete graph is? You can answer the question in general or just try for one complete graph like K5. And then what do you think the vertex covering number of a complete bipartite graph is? Again, you can figure it out for this example or in general. All right, here are the quick informal solutions. In a complete graph, by definition, every pair of vertices is joined by an edge. So if there are 2 vertices that are not in our vertex cover, for example, maybe we try to make a vertex cover with U1, U2, and U3. Here, there are 2 vertices not in the vertex cover. Since this is a complete graph, we know that they're joined by an edge, and so, oh no, it turns out this wasn't a vertex cover to begin with. So the idea is for a complete graph, if there are 2 vertices not in your set, then that set can't possibly be covering all edges of the graph, and so certainly the vertex covering number of a complete graph is going to be 1 less than the number of vertices, so long as the number of vertices is greater than 1. As for a complete bipartite graph, by definition, every edge in such a graph goes from one set to the other, right? It's bipartite. Thus, as long as you have all vertices from one of the partite sets, every edge will have to be going from one partite set to the other, and so you're guaranteed to have all edges covered. Now, since you can cover a complete bipartite graph by taking all vertices in either partite set, for the minimum covering number, you'll want to take all the vertices in the smaller partite set. So we can say the vertex covering number of the complete bipartite graph, KRS, is equal to R, where we'll say that R is the cardinality of the smaller partite set, and they're both at least 1. The last two things I'll mentioned is that if a graph has no edges, then any subset of the vertex set would technically be a vertex cover. And secondly, we're guaranteed that every graph does have a vertex cover because you can't have an edge without having incident vertices. So certainly, if you just took every vertex from a graph, that would always be a vertex cover. And that's it. Again, a vertex is said to cover its incident edges. Then a vertex cover in a graph is a set of vertices that covers all of the graph's edges. A vertex cover of minimum cardinality is called a minimum vertex cover, and the number of vertices in a minimum vertex cover is called the graph's vertex cover number, which we will denote beta of the graph.
Got a nest in my chest for the dreams of sleeping beauty. Slow and hard, needing rest from the riots and the looting. Got a pain that shot.
It's actually not hard to understand how it works.
Hey everybody, I wanted to give a description of the minimum vertex cover problem in a graph.
It's gonna be hard to rewrite this stuff here. I think this part I'm gonna remove because it's not something I would say, I think. And like the second part I wouldn't put, I think. And the first part is just redundant because it's talking about what was talked about here. I'm gonna remove this thing here. And this part, I think I'm gonna rewrite it and leave it here. Let's see. And this is stuff that I hate, so obviously I'm gonna because why not make it easier? What the fuck is going on? Maximum independent set is in a graph is a subset of nodes such that no two nodes in the subsets are connected. That doesn't make sense. Yeah, I think I studied this because there is an article about this thing here, I think. I remember seeing this concept. Okay. So there are nodes that are not connected through But they have intermediary nodes between them. I think I understand. Maximum independent set in the graph is a subset of nodes such that no two nodes in the subset are directly connected by an edge. Complement of a minimum vertex cover is a maximum independent set. And vice versa. This means that if you know the size of a maximum independent set in a graph, you can find the size of a minimum vertex over by subtracting it from the number of nodes in the graph. So I think it makes sense because the nodes that are going to connect all of them are the intermediary of the nodes in the independent set. So independent set are nodes that are connected through other nodes, so they don't share an edge. And because of that, the nodes that connect them have all the connections. That's why they are the minimum vertex cover. So they are complementary. I think I understand. This means I have no the size of the maximum. These have all the edges. The set is a graph. A graph is a subset of nodes such that no two nodes in the subset are directly connected by an edge. Complement of a minimum vertex cover is a maximum independent set and vice versa, because in the maximum independent set the nodes don't share edges, so it means they are connected through intermediary nodes. Therefore, let me see if this word is correct. Intermediary. Therefore, those intermediaries will be the minimum amount of nodes that contain all the edges of the graph, making them the minimum vertex cover. Means that if we know the size of maximum independent set in a graph, we can find the size of a minimum vertex cover by subtracting it from the number of nodes in the graph. I think that's good enough. Computing the minimum vertex cover of a graph is an NP hard problem. This means that there is no known polynomial time algorithm that can find the minimum vertex cover for all graphs. However, there are polynomial time approximation algorithms that can find an approximate minimum vertex cover with a guaranteed ratio of approximation. I think I'm not going to change this. I don't see the point. Like, there's nothing seems to be correct, and I don't know. Like, there's nothing I would say differently here, I think. Bipartite graphs have a simple solution. In a bipartite graph, a graph where the nodes can be divided into two disjoint sets. This is the graph that is used for arbitraging decentralized exchanges, because you have the tokens and the exchanges. So I'm familiar with this type of graph. Such that all edges go between the sets. A minimum vertex cover is equivalent to a maximum matching. Maximum matching. I also think I've seen this before. I don't remember really well. Set of edges shows in such a way that no two edges share an endpoint. A maximum matching is a matching of maximum size. Okay, I think I remember this. And there's something to do with the cycles as well. On some of the algorithms that I think is one of the algorithms where it finds the maximum matching, or it finds the cycles based on maximum matching because the cycles are the opposite of the maximum matching, I think. There's something like that, I don't remember really well. And maybe it's this Hopcroft or whatever the fuck. Or the Ford Fulkerson. I think it's the Ford Fulkerson that I've seen this. Yeah, maximum flow. And this Hopcroft I don't have here. What I'm gonna do as well here is to put and then I have to find the link to this. Oh, also something that I figured out that is related to, I don't think I'm gonna go back to redo the video, but I realized that the problem is not with the Next.js link, it's just that I didn't understand how it works really well. But when you don't put the backslash here, then it goes to the relative path from the path that you're at right now. But if you put it like this, then you can go to the absolute path from the root of the thing. And I didn't know that. But either way, on the problem there, on the video, like, it still holds true because the problem is fundamental. Is the difference in the data changes, but the linking stays fixed. And in order for you to be able to have all the routings for the blog or whatever you're doing, the link has to be as dynamic as the data flow of the not sure what's the right word, but the variability of the data. So the more the data varies, the more the link has to vary as well. And that's, so the more levels you have, the more dynamic the link has to be. So either way, it doesn't matter if you put the link from the root every time or from the relative path, because the problem is the same, where the link is not dynamic enough. And then to solve that, you modify you did the thing that I did there with the get static props, of modifying the route based on the props you get, based on the path you receive. Yeah, this makes sense as well, I think, because they are connected to two different sets, So the minimum vertex cover is going to be equivalent to the maximum matching, because they are both the ones that are connected through intermediary nodes. Okay, I think this makes sense. So, and I think this also is true because I've seen on the Geeks for Geekstar. So I think I'm gonna leave it like this. I'm just gonna go to this article and see if the link works there. Yeah, it does work. Not sure why it's because of the links. Yeah, maybe I will change this in the future, because these things you change on this. The way that I'm doing this project, I'm using the theme UI, so I change here on the styles, and I change the size for H2 and H3 and H1, and also for this B here, so that changes the size of the text on the normal thing there. The P is the one that changes the size of the text here. But then if I want to change here, I'll have to put Lee here and then change it. Maybe I'll do this now. I think I'm not sure, because it might be a good thing to have the Lee as, I think it looks better like this probably. Yeah, because then it's easier to have a difference, and then if I want the text to be bigger, then it's gonna be too big. Maybe I'll do this, but then I'll put smaller sizes. Yeah, this seems fine. I think this is stuff that I'm gonna worry about way later. I'm also thinking about the whole SEO and the optimization of the functions. Like thinking about the caching, and I also thought about creating a context. And then instead of using the props to get the articles of the current page, I can use context, and then, because I'm not really sure which one is the best, I'm thinking about, because I don't understand really well how the Next.js works under the hood, if they optimize with caching for loading the pages. I assume that's the case with the get static props, because otherwise what would be the point of having, like, there is a different point, I think, is because you don't need the database, but I think that they probably optimize with caching. So instead of requesting all the routes and activating the function each time you access a page to see which articles are going to exist, you make some form of caching in the beginning so that it's more efficient for the user. But I think it doesn't make that much difference. But the one that makes a difference, I think, is the one that gets all the paths, because the more articles I have, the bigger and slower it's going to be. So ideally I would think about a way to make that more efficient. But then for loading the graphs itself, I think that is not a big deal, because it's always going to depend on the category, and because I'm splitting everything on categories, it's never going to get too big, I think. But this is stuff for way later, I think. Like, it doesn't matter now. It's much better to focus on writing the content. So let's go to here. It's actually a lot easier than I thought that it would be. I think it was just the way that it was written that was confusing there. But it's not hard to understand at all, actually. I remember seeing this linear programming as well when I was studying the arbitrage problem. There are a bunch of different solvers. There's linear programming and then quadratic programming, I think. But I don't remember really well. If I'm not mistaken, maybe it's the other way around, but I think that this means that it is the space that goes from 0 to 1, containing all the values, and then this contains 0 and 1, or something like that. I think I'm gonna see the other parts of this first, and then I'll go back to this. Because I wanna spend more time on this one. Then it's probably better to just see the rest, see if there's anything that's gonna be more difficult to understand. Then to stop here and, you know. And this is interesting. I think I'm gonna try to get another algorithm for this as well. I think this is fine, so the three things that I'm gonna do is just review this stuff here, this one, and then change the algorithm, I think. It should probably finish today, for sure. And then after that, I'm gonna start on the data structure ones. Yeah, let me watch this video.
This is an integer program where you can approximate the solution via a linear program relaxation. Okay, so capital G is our graph drawn here. It has a vertex set, capital V, and all of these points are the vertices. And then it has an edge set, capital E, and all of these are the edges. So in the minimum vertex cover problem, what we're trying to do is we're trying to find a collection of vertices. We'll call it S. It's a subset of our vertex set, where every edge is adjacent to at least one vertex in our set S. So let's try to find a possible vertex subset S. You can take all the vertices, and then certainly if you take all the vertices, every edge is adjacent to at least one of those vertices, but we're trying to find a minimum vertex cover. Okay, let's just try to find one by hand. I won't claim to find the optimal vertex cover, but let's just let's try to do a reasonably small cover. So let's say I take this first vertex. That means all the adjacent edges are handled. So I'm just going to cross out those edges. Let's see. Looking here, this edge, since this edge has not been covered, I'm going to need to choose eventually one of the two vertices. Why don't we just choose the top one? Okay, so let's add this vertex to our set S. So that covers this edge, and this edge. This edge is now handled twice, but who cares? We just need to make sure that every edge is handled at least once. Over on the left side of the diagram, I think I'm going to need to select two of these three vertices to cover the edges. So I might as well select this one, because I get that edge as well. And then why don't I select this vertex, which covers that edge? Let's keep going. Maybe I'll select this vertex to cover that edge and that edge. And I'm getting there. Maybe I'll select this vertex so I cover those two edges. And finally, I can select this vertex to cover those two edges. So you can see that all the edges are covered by at least one adjacent vertex. So let me erase all of our, let me erase all the scratch work on the edges. Problem. But furthermore, we'll specify that the variables have to be integers. Okay, so x sub v is going to be a variable associated with each vertex little v, which is 0 if it's not in our set, our cover, and it's 1 if it is. So we're trying to minimize the number of vertices in the cover, which means we're trying to minimize the number of vertices that obtain the value 1. That's equal to the sum right here, the number of vertices in a cover. Subject to the linear constraint that for any edge going between vertices u and v, at least one of those vertices u or v has to be in our cover. So you can write that by saying that the sum of xu plus xv has to be at least 1. At least one of those variables has to be 1. Otherwise, this edge is not covered. All right, so we have a linear optimization function, we have a linear constraint and inequality, and then we furthermore have this requirement that our variables are integers, in particular either 0 or 1. And that's why this is an integer linear programming problem. It's been proven that solving this problem is NP hard in general. So for a general graph, you expect it to be hard to find the optimal vertex cover. This is considered a medium hard integer linear programming problem in the sense that we'll find an efficient way to find an approximate solution, an approximate optimal solution, I should say. It won't be necessarily optimal, but it'll be optimal within a factor of 2. So let me write here LP for linear program, in particular the LP relaxation. So all we're going to do is we're going to relax this integrality constraint. And so this integrality constraint is going to instead be that each variable x sub v associated to a vertex little v. I want to give x sub v, solving this linear, we're going to make a valid vertex cover. We're going to point 7 up, so this vertex is. Well, on each edge we have this constraint. Text in R, therefore valid cover as LP. And now I want to argue why the second is the not necessarily. Okay, so this is by the. Sure, how will I explain that? That's okay. Into the integer programming problem, a valid solution is. All right, and now this is just all these variables.
I think I'm going to stop here actually.
The moral of the story.
And I'm going to I'll use ChatGPT for the algorithm. I'm probably gonna use ChatGPT as well to write stuff explaining the algorithm as well. And then I'm gonna study these two things here as well to make sure that it makes sense and it is accurate. And I might change the text, but probably not. And yeah, after I finish this two here and the algorithm, then I'll start the data structures. I think I want to finish these first, all of them, the articles, and then I start reviewing them. Maybe today, but probably not. Probably tomorrow. So today I'll just finish this article here, and then finish these other ones here. And then I might start reviewing them off stream as well, or maybe, yeah, depends on how I feel. Because after these ones, then I'm going to start the 3 algorithms, I think. Yeah, so we'll see. But I think I'm gonna stop here and yeah, probably come back tomorrow. But maybe small chance that I come back today just to continue to review these articles here. So yeah, see you soon.